Have now Paul Heslop from Durham, and he will talk about amplitudes and
Wilson loops in special kinematics. Okay, thank you very much. Thanks again, Adam, and thanks to the organisers this great workshop. Okay, so this is based on work with Valia Koza. And it's going to be on these papers. And then at the end I'll include some work, sorry. I knew I'd forget to do that. Include some work with my student Tim Goddard, which is work in progress. I'll just make a few comments there. Okay, so this sort of carries on nicely from Mark's talk the other day, where he introduced scattering amplitudes. So I'll do an introduction, but hopefully I can skip fairly fast over some of the things since they've been talked about before and introduced before. So the point is, there's been much progress. Well, for a long period of time, but especially over the last few years in perturbation theory in n equals 4 super Young-Wills. So I'll be discussing n equals 4 super Young-Wills, SUN gauge group, and I'll be in the planar limit. And I'll be discussing scattering amplitudes, and in particular I'll be focusing until the last bit, I'll be focusing on MHV amplitudes. Okay, so there's been a lot of progress in a number of directions, and there's been a lot of progress in particular at the level of the integrand. So for a number of years people have been looking at generalized unitarity. As a method for getting integrands for amplitudes, and then more recently the idea of leading singularities, and BCFW, a generalized BCFW, came into being from work with Nima Akani-Hamed and Kachazo and friends. They generalized BCFW, tree-level recursion relations, to obtain integrands at loop level. Okay, so there's been a lot of progress in that direction. There's also been progress at the level of the integrals themselves. So so at some point you have to actually do the integrals. So there's a two-step process traditionally, and both steps are hard. And there's been a lot of progress in the first step, obtaining the integrands. And the second step still has to be done, and it's almost like a separate stage of the problem. So then there's also been progress at the level of the integrals. This has been well, it's been quite rapid as well, but obviously it's not gone as far as the progress at the level of the integrand yet. So I want to discuss this part of the problem, and in particular I want to see if there's a way of sort of bypassing this two-stage progress. First of all, finding integrands, then integrating them, to sort of try and constrain or derive the amplitudes at the level of the integrals themselves. Okay, so I'm talking about, as I mentioned, MHV amplitudes. So we've got some MHV amplitude. Has two negative helicity gluons, and the rest are positive helicity gluons. And what you can do is you can take the MHV amplitude, divide it by the tree level amplitude, and obtain something which is often called M at endpoints. And the point here is that this is just a function of the momenta, together with the coupling constant and well, also you have to regularize it. So there's a regularization parameter floating around as well. So what I'm going to do, I want to try and, in a series of steps, constrain the amplitude as far as possible. So, the first step in trying to get more structure for the amplitude is to consider this property of dual conformal invariance. Okay, so there, instead of taking this amplitude mn, I consider the following object: log of mn minus BDS at endpoints, and I define this to be some sort of remainder function. Okay, now this does two things. First of all, it's a finite quantity, so this plus order epsilon if I'm doing dimensional regularization. So it's finite, and it has dual conformal invariance. Okay, so let's just spend a moment discussing what this dual conformal invariance is. Again, it has been talked about by various people, but just to set the scene. So we've reduced the problem so far to a function of momenta and the coupling constant. Now the dual conformal invariance, in order to do that, it's easiest to talk about this amplitude Wilson loop duality. So that's a duality between amplitudes. So they have momenta P1, P2, P3, and so on. Instead of discussing an amplitude, or an MHV amplitude, let's say, I can discuss a Wilson loop. And the edges of this Wilson loop are P1, P2, P3, and so on. So I just put these momenta end to end. And now this is a Wilson loop. So this is the contour of the Wilson loop. And this has, at least if it was a smooth Wilson loop, it would have conformal invariance in n equals 4 Young-Mills. In other words, if I did a conformal transformation on it, I should get the same answer. Now this has cusps, it's divergent, but this remainder function still has the property that it's finite and has this conformal invariance. So the main point here is simply to define the region momenta. Again, these have been defined before. And again, as Lionel did, I always end up drawing them the wrong way around. But the algebraic relation is that P1 is at x1 minus x2. To draw them the right way around, you have to have them the arrows going in the reverse direction, I think. Okay, so this is a light-like polygon, and we can consider the Wilson loop of this thing. Okay, so what have I done? I'm now discussing a remainder function as a function of x's. These region momenta, which are defined like this. So pi is xi minus xi plus 1. And of course, it's still a function of lambda. Okay, so this is a hidden dual conformal invariance from the amplitude. This is something you'd never think of doing originally from the point of view of the amplitude, but on the Wilson loop side, it's a perfectly natural symmetry. Okay, so we've got this function, and essentially it's equal to a function of Lx1, Lxn, lambda, where L is some conformal transformation. Okay, so the next stage in trying to constrain our amplitude as far as possible using as many symmetries or structures as we can is to try and solve this. Is to try and, if you like, solve this conformal transformation. So what you do there is you define some variables which are invariant under the conformal transformation. So we define cross ratios. So we have a function of x1 mu up to xn mu. So in principle, there are 3 n minus 1 variables here, in fact, because, well, really, you've got n minus 1 like p's. And then we go to cross ratios, uij, which are defined in a certain way, xi minus 1 j plus 1 squared, xi plus 1 j minus 1 squared, divided by xi minus 1 j minus 1 squared, xi plus 1 j plus 1 squared. And there are n times n minus 5 over 2 of these, which doesn't look like a very good reduction at first sight. Now, it turns out that these, of course, are not independent, so there are relations between the u's. And that brings this down to 3n minus 15, which is more what you would expect. So I have 3n minus 1, I subtract off, essentially I'm subtracting off the conformal group. I end up with 3n minus 15. However, this number is the number of uij's is somehow more important. It turns out that the fact that variables are independent, for what I'm going to do in a moment, is not so important. It's more important that logs of variables are linearly independent. So I'll discuss that in a moment. But yeah, these uij's in some sense can be thought of as independent variables. I'll come back to that point. Okay, so we've reduced things down, but we want to go further. Well, sorry. First, let me. Shall I use this one? First, let me discuss the implications of what we've discovered so far at low numbers of points. So at 4 and 5 points. At 4 and 5 points, we see that using either of these numbers, in fact, we have 0 cross ratios, or, well, actually, if you put 4 in, you get a negative number. So there's essentially no dependence left. So at 4 and 5 points, the remainder function is a constant, or appropriately defined as 0. And another way of saying the same thing is that we know at least the log of the amplitude. To all orders. At least in principle. This I didn't say much about this, but this is a known quantity. It involves the one loop amplitude, and it also involves this thing that keeps cropping up, the gamma cusp, which is a property which people, at least in some sense, know to all orders in perturbation theory. Okay, so 6 points is the first non-trivial case, and in particular 2 loops is the first non-trivial case. Again, because this thing depends on one loop, essentially the remainder function at one loop is trivial and vanishes. So 6 points, 2 loops is the first non-trivial case. Okay, so then we come to this this thing that Mark talked about, this 17-page formula that Del Duca, Durham, and Smirnov found. So DDS, they calculated this. They calculated the Wilson loop rather than the amplitude, and they got 17 pages of Goncharov polylogs. And that was simplified by GSVV, Goncharov, Spradlin, Vergu, and Volovich, down to a sort of, well, depending on how small the font is, either 1 or 2 line formula. And that involved Li4s and so on of u's, 1 minus u's, and then complicated square roots square roots of u's. Okay, And the point, the thing that I will take from this is the symbol, which Mark discussed a little bit in his overview talk. The method for doing this was the symbol. It's sort of new, or at least new in our field, mathematical technique for simplifying or trivializing polylog identities. Okay, so now this is not, in fact, the main starting point for what I'm doing. I'm going to take the symbol from here, but this by itself is not the main starting point. So I want to simplify things even further. So instead, I take a paper which I'd had to recall the history of events actually, because this paper came in the same month as the GSVV paper. It was another Del Duca Dor Smirnov paper, and what they calculated was an 8-point two-loop remainder function, and they calculated it in special kinematics. And this simply means in 2D kinematics, 2D external kinematics. So the x's, so we've got an R8 of 2, it's a function of x1 up to x8. And I just simply insist that my x's lie in 2 dimensions. So again, this is a loop level object we're trying to calculate. So the particles in the loop still lie in 4 dimensions or d dimensions. But I just insist that the external kinematics lie in 2 dimensions. Okay, now if you do that, then the number of cross ratios reduces. In the 8-point case, you essentially get a cross ratio U15. This is notation that this is still using this notation Uij. You get a U26. You get a U37, which turns out to be 1 minus U15. Sorry, this is 1 minus U37, and I get a 1 minus U48. So there's 2 independent variables, or 4 cross ratios, and this is what I mean by independent cross ratios. The log of U15 is somehow independent, it's linearly independent from log of 1 minus U15. And the result they got was that R8 of 2 was equal to minus a half log U15, log U26, log U37, log U48, and then there's a constant, plus pi squared over 6. So in actual fact, when they were doing this, they started off with an expression which was much more horrendous than even the starting point for this expression. I mean, they actually did a lot of simplifications to get down to their 17-page formula. This was before the symbol. They were implementing lots of polylog identities by hand. They did the same thing here. They started off from a much bigger expression, but this was pre-symbol again, remember. And then I guess because the final answer was so simple, they were able to, in fact, implement it all before the symbol came along, down to this very simple formula. So this is now the starting point for my investigations. I want to consider this simple structure. I want to consider 2D special kinematics, and see how far we can get by investigating amplitudes in this special kinematics. So let me say a little bit more about the special kinematics. So the 2D kinematics was first considered at strong coupling by Alde and Maldacena. In fact, the first non-trivial strong coupling result was precisely this 8-point special kinematic result at strong coupling. That was the first non-trivial strong coupling result. And then, so that was Alde Maldacena. All right, special, if you like. at strong coupling. And then it was Olde, Maldacena, Seva, and Vieira, and they did endpoint at strong coupling, both in special kinematics and in general kinematics. And the point I want to make here is that the special kinematics was given by a Y system, and the answer, the remainder function, if you like, was basically the free energy of this Y system. And in general kinematics, it's just a slightly more complicated Y system. And again, the answer was the free energy. So the point I'm trying to make here is that the special kinematics sort of contains somehow the essence of the result at strong coupling. But it makes the kinematic stuff a bit simpler. And I kind of view it a bit like the SU2 sector for the dilatation operator. It's a sort of subsector to look at first in order to, if we want to sort of get some insight about integrability or whatever, then it might help to consider this sector and remove some of the complications of kinematics from maybe some of the other insights. So that's the sort of motivation. Okay, long motivation. Okay, so let me draw a picture of the special kinematics. Maybe I'll use a new board. So this special kinematics lies in 2 dimensions. So I can draw it on the blackboard without having to hide any dimensions. We're discussing a light-like. Well, we're discussing an amplitude, but if I view it as the Wilson loop, I'm discussing a light-like contour. So all my lines need to lie in 45-degree angles. So I get this sort of thing. We normally go up and down. I can also go in this direction if I want to. That only causes some analytic issues, but I have to do that to close the contour, unless I do some things at infinity. So now what I do is to set up this thing, I discuss light cone coordinates. So I somehow draw my axes like this, and then I'm going to label it. This is my x1, this is my x2, this is my x3, x4, x5, and so on. And I'm going to give that a light cone coordinate z1, and I'm going to give this a light cone coordinate zn. I'm going to give this a light cone coordinate z3, and I'm going to give this a light cone coordinate z2, and so on and so forth. So somehow the plus light cone coordinates correspond to odd z's, and the even light cone coordinates correspond to even. So the plus light cone coordinates correspond to even z's. Or to put it another way, I have x1 is equal to z1 comma zn in light cone coordinates. x2 is equal to then z1 z2. x3 is equal to z3 z2, and so on and so forth.
So those are the momentum twisters.
That's the next point, yes. Good, yeah, no, exactly. So these are precisely the momentum twisters, in fact, in the reduced kinematics, which is somehow the motivation for this this notation. I mean, the other choice, what people often use is z pluses and z minuses, just to distinguish the plus and minus light cone directions. But I think this is actually, one of the main problems is that it kills the cyclicity. The cyclicity, with these z's, I maintain cyclicity. If I choose pluses and minuses, the cyclicity is a little bit obscured. And the other thing, as Lionel just said, is the momentum twisters. So, so first of all, let me discuss. We want to have things like xij squareds in the game. We want Lorentz invariants, and these just become zi minus zj multiplied by a zi minus 1 minus zj minus 1. if I and j have the same parity. Or they can become a zi minus zj minus 1 times a zj minus zi minus 1. Possibly with a minus sign. You have to check the minus sign. So this is if I and j have the opposite parity. And then you can easily, and then we use the notation Zij is Zi minus Zj, and we write that as Ij, for reasons that will become clearer in a second. So let's just compare with momentum twister. So I've done everything from a space-time point of view so far. From a momentum twister point of view, so momentum twisters are another way of well, as Lionel explained yesterday, so they're another way of parameterizing the remainder function. You can discuss it as a function of momentum twisters. So I have a Zi, and in 2D kinematics, this is my momentum twister. It's a four vector or a 4 component object, and it has a 0 here and a 0 here, and a non-zero there and a non-zero there. In special kinematics, that's the reduction. And now, because this is a projective object, I may as well call that 1 at the expense of losing out on infinity. But apart from that, I don't lose much. And if I then call this zi, little zi, then I get the map between these z's and those z's. So this is zi when I is even, and then when I is odd, I just get the other one, 0, 1, 0, little zi for I odd. And if I didn't do this, if I didn't rescale this to 1, you'd see that what I define as ij is in fact just the 2 bracket, the standard 2 bracket of this 2-component object. Okay, I mean, these aren't spinners, which is what we normally think of as an ij as a thing of spinners, but nevertheless I can take over the notation. Okay, so what about cross ratios in this in this thing? So the cross ratio is reduced to essentially ordinary cross ratios in CP1. So the uij reduces to I minus 1, j plus 1, I plus 1, j minus 1 divided by I minus 1, j minus 1, and an I plus 1, j plus 1. And indeed, for the twistorial people amongst you, a uij is an I minus 1, I, j plus 1. So this is what a cross ratio looks like in momentum twisters. And the basic point is to get from here to here, I just cross out I and j. I find a common, in every bracket I have an I and a j. I cross out the i's and j's and I get this guy. That's the sort of rule of thumb for going from one to the other. So uij is this is only valid if I and j have the same parity. And it goes to 1 if they have opposite parity. Okay, so these are the variables in the game. I've got the variable z's, and then I find that if I want to incorporate conformally invariant quantities, then fairly obviously I have to consider cross ratios of the z's. I have 2 sets of z's, the even z's and the odd z's. So I've basically got I've got 2 copies of a CP1. And these 2 things are, so these 2 copies are largely independent, but the cyclicity entangles them in some way. I mean, the cyclicity affects both the even and the odd guys. So they're entangled by cyclicity, but in other ways they're largely independent. Okay, one other thing I should say is, so I can, of course, define a more general cross ratio of the z's now, which is ijkl divided by iljk, and these satisfy the following. So I mentioned that there are some identities between cross ratios, and this identity in 2D kinematics becomes a very simple identity, namely this one. Which you can view, it's easier to view that using a picture, I think. I've got an I, a J, a K, and an L, and then I have an IJKL divided by an ILJK, and that's equal to 1 minus the guy where you have the same denominator but the different numerator. 1 minus this guy. It's just a standard Shelton identity in 2D. Okay, so the main point I wanted to make is, first of all, that there's a reduction in kinematic complexity. The momentum twisters were useful for trying to sort out some of these square roots that one got in the amplitude. Now we see that here there's less of a difference between the momentum twisters and the space-time points. They're essentially the same thing. So the cross ratios of twisters that you tend to obtain just become standard cross ratios in 2D kinematics. So we make the following starting assumption and investigate what happens under this assumption. We'll assume that the remainder function is given in terms of polylogs with argument which are used, essentially. And this seems to be consistent with all results known so far. It may well break down at some loop order, but we just have to see, I guess. So let's assume that for now, the polylogs with arguments used, or the modern way of saying that would be, what I really mean by that is I make an ansatz for R of Z1 up to Zn at L loops. Well, I'll only discuss 3 loops, but let's be bold. And I say that this has a symbol whose entries are simply logs of cross ratios. Okay, I mean you have to know a little bit about the results in general kinematics to see that this is a non-trivial assumption. In general kinematics, I think I mentioned you get functions of u, you get functions of 1 minus u, and 1 minus u in general kinematics is not related to u, it's independent. At least log of 1 minus u can't be written in terms of sums of log of u's. I don't have any identity like this. And then you also get square roots, complicated functions of square roots. All of these reduce down to u's in 2D kinematics, so that sort of motivates this assumption. Okay, well let's use that assumption and see how far we get. Okay, so I have to really, I think, talk a little bit about the symbol because Mark introduced it a bit, but maybe it was quite quick. I thought his introduction was quite quick. I don't know, people who don't know. Sorry?
I'm going to do that at next talk as well.
Well, I'm sure you will, and probably James will as well. But I'm first, so.
Yeah, but I invented it, right?
Okay, well I'll just. Well, but I'm using it, so I have to use it. When there's a causality problem here. So let me just write down one formula to illustrate the symbol. So Li n of x is given by an iterated integral, and of this sort of object, d log Tn, d log Tn minus 1, d log T1. So to understand that a little bit, let's just think about Li1x first of all. Li1 of x is minus log 1 minus x, that's just the definition of what it is. And I can write that as the integral minus the integral of x of d log 1 minus, it should be a 1 minus somewhere. Oh, that's the first one here. This is 1 minus Tn, and d log of 1 minus Tn, let's say. Okay, here it's a fairly trivial thing to do. I sort of integrate and differentiate. But then the next one, Li2, is given by differentiating Li1, so integrating Li1, and so on and so forth. So this is simply a way of writing the definition of Li n of x. Now what the symbol does, as Anastasia will also tell us tomorrow, not tomorrow, today, this afternoon, is that I replace this with a minus d log 1 minus x tensor d log x tensor dot 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 tensor d log x. Okay, so you can see the structure coming in here. The x comes about because that's the thing. Eventually, it's only a function of x. All the other integrals are just are integrated over. And instead of considering this function, I consider this tensor. And then people drop the d log, so people write 1 minus x tensor x tensor dot 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 x. So okay, I actually want to keep the logs in. I'm not so bothered about the d's, but I like to keep the logs in the definition of the symbol, because then it clarifies the linear algebra. You know, the fact that it's a tensor. It's clear if I keep the logs in. So, for example, I just have the standard property of a tensor that it's linear in its arguments. So d log tensor d. If I have a d log ab in the middle, then this is a d log a plus a d log b, obviously, because that's what we know. And now, because this is a tensor involving a sum in the middle is just the sum of the tensors. So this is just a d log a tensor plus tensor d log b. So the main point is that this is really a tensor. And so what this does, this great insight of Anastasia and Mark Spradlin and Gontroff and Vergu, is it reduces the problem down to essentially a linear algebra or a multilinear algebra problem. Okay, I now, instead of having to discuss complicated functions of polylogs, I just have to discuss tensors. Tensors are something I can deal with. Of course, the point I haven't mentioned is that this of course trivializes polylog identities. Okay, but I'll leave that for now. Now, if we have if I say this is a multilinear algebra problem, then one thing it's nice to understand is what is the vector space? What is the, if you like, what is the basis over which my tensor is constructed? is the basis? Okay, now under my fundamental assumption that I'm assuming only logs of u's come about, then I can claim that Lij, which I define as d, well, again, I'll probably leave out the d, but it's essentially just log of uij is a basis Okay, so first of all, it spans. It's a spanning set. This is because any cross ratio uijkl can be constructed as a product of these uij's. So uijkl equals a product of uij's. So any most general cross ratio is a product of uij's, and therefore the corresponding log of uijkl is a sum of these lij's. So I don't need to consider this guy, I only need to consider this. This is a basis. And then the other thing I need to check is that it's independent. So the lij's are independent. So this was the point I sort of mentioned earlier. The lij's can have arguments, so they're not functionally independent, but they are linearly independent. Sorry, I should write that, linearly independent. So in other words, I can have a log of a u and a log of a 1 minus u. Now these are, have dependent variables, but as in terms of this vector space, these are linearly independent. Okay, so it's very useful to have a basis when we're considering vector spaces. And now I come to the method for actually computing things. So we've got the setup. I now need a bit of input. So I can immediately write down in ansatz now, given my assumptions and given the constraints that I've described. I write down in ansatz, for example, for 2-loop endpoint. And the ansatz is that Rn of 2, or more precisely the symbol of the remainder function, is a sum with some coefficients, ai1 up to i8, of some lij's. Lij's are the logs of the uij's. li1 i5, li2 i6, li3 i7, tensor L i4 i8. Okay, why does it have rank 4? Again, this is another assumption that goes in, that's been observed in A equals 4 Yang-Mills, is this transcendentality principle, that we get polylogs of weight 4. And the rank of the tensor gives the polylog weight. So that's why it's a 4 tensor. Okay, so we've reduced the problem essentially to linear algebra, and in particular we need to determine these coefficients. So the various further constraints we can have, there is cyclicity and parity. So in terms of the z, cyclicity says that Rn of z1 up to zn is equal to Rn of z2 up to zn, comma z1. And then parity just says that if I flip the order, and this is equal to Rn of zn down to z1. So that clearly reduces the number of independent constants. But the main thing that helps me to reduce the independent constants is the collinear limits, or soft limits, soft collinear limits. Okay, so the collinear limits is very simple in this picture. We have we have this zigzag. We have the zigzag Wilson loop. I had these z, so this would be zn minus 2, let's say. This would be a zn. And I consider the limit where this goes to 0. So it's a soft limit. My momentum is going to 0, but at the same time as being a soft limit, these two lines also become one big line. So it's kind of a triple collinear limit and a soft limit. So this goes to boing. There's a point there, boing, boing like that. And now this point here is a zn minus 1 in my notation. So this special point here is a zn minus 1. And one of the key features that enables you to get information out of this is that the function has to be independent of zn minus 1, despite the fact that you haven't done anything to it. The only limit I'm taking is zn goes to zn minus 2, and the function has to become independent of zn minus 1. So in an equation, I have the following constraint. Oops. So Rn of z1 up to zn, in the limit zn goes to zn minus 2, has to reduce to Rn minus 2 of z1 up to zn minus 2. Okay? And the point I just said is that zn minus 1 has to disappear without you telling it to disappear. So that constrains the form of your remainder function. I should say that this is not obvious. This is another very nice feature of the remainder function. I mean, normally for amplitudes in the collinear limit, you get splitting functions and so on and so forth. The splitting functions are taken care of by the BDS ansatz. And so the remainder function has these very nice collinear properties.
But don't we have a jump by constant? It's a triple solution.
Yeah, no, sorry, you're right. So there is a constant here as well, yeah. But what we kind of we take care of the constants. We redefine the r's so that the constant there's a constant there, but it's somehow the complicated bit is the functional form. So we redefine our r's to get rid of the constant. But I'm sometimes a bit sloppy and I don't do that. Well, it's also true that the SYM. No, but we don't actually. That's an important point. We the thing we write is for functions. Okay, so let's start trying to do this. So let's consider R6 first of all. As Andy just said, R6 is a constant, and for me this constant is 0 because I redefine my remainder function such that it's 0 in special kinematics. This is, of course, why we consider 8 points. Okay, R6 is trivial. So R8 has to reduce to R6, which is 0 in the collinear limit. Okay, it's supposed to be a tensor involving the following variables. It involves the L15, which is the log of U15, L26, L37, and L48. And in the collinear limit, it's very easy to check. In the limit 8 goes to 6, then we have that L37 goes to 0, and correspondingly L15 goes to infinity. So what this tells me is that as soon as I want to have an L15 in my tensor, I get an infinity. I'm not allowed to have an infinity in the collinear limit, so therefore it has to be suppressed by also having an L37, which kills the infinity. I mean, this 0 is a log. This 0 is a log 1, and this is a log 0. So the 0 kills the infinity. Now, however, I can also consider a different collinear limit. So let me just try and write that down. So if I have L15, I also need L37. But I can consider another collinear limit. 6 goes to 4. And there it's the other way around. I have L15 goes to infinity, and L37 goes to 0. So therefore, conversely, if I have L37, I also need L15. So I need both. I need L15 and L37. And then I can consider collinear limits with the odd variables going, and I get the same statement. So you end up by saying I need all 4 of my cross ratios. I mean, another thing that I'm using here is that I can do these limits at the level of the symbol. I can consider if the symbol has a 0, then it means that the corresponding function goes to 0, or at least goes to a lower transcendentality function. So the conclusion is that R8 2 loops is equal to some constant times L15, this is the symbol, times L26, tensor L37, tensor L48, plus, and then I have other constants with arbitrary permutations. Permutations, but the constant can be arbitrary, so I have 4 factorial constants. Okay, now I implement cyclicity. So there's 4 factorial constants here. Cyclicity and parity kills 8. It divides by 8 essentially, because cyclicity gives me 4, a cycle 4, and then parity gives me another 2. So I end up with 4 factorial divided by 8 is equal to 3 constants. So I get 3 orbits, if you like. And then finally, I use a fact that I haven't mentioned, and I'm sure Anastasia will mention this, that an arbitrary tensor is not necessarily the symbol of a function. So there's this so-called integrability constraint that you need to satisfy. And that essentially kills these 3 constants down to just 1 overall constant. So the integrability constraint, again, I don't want to necessarily say too much if Anastasia is saying more later, but for example, log x tensor log y is not the symbol of any function if x and y are completely independent variables. Whereas log x tensor plus log y tensor log x is the symbol of simply log x times log y. So there's this integrability constraint relating wedge product of nearest neighbours that a symbol has to satisfy in order to be the symbol of a function. So it's not good enough to just write down an arbitrary tensor. It has to satisfy a further constraint, and that reduces these 3 constants down to 1 constant. And in fact, what it ends up doing is it simply says that these coefficients are all the same, plus permutations with coefficient 1 each time. And in fact, this is simply the symbol of the function. This is a tensor, but this is the symbol of the function a times L15 times L26 times L37 times L48. And this was the Del Duca-Dur Smirnov result, plus a constant, which, as I've said, I've removed. Okay, so that's a sort of derivation, if you like, within our ansatz, within our assumptions of their result. But then we can lift to higher n using collinear limits, or if you like, inverse collinear limits. And the answer is simply, or what I could say is an answer is this. I have an alpha. In fact, this alpha is the same as this a. This coefficient, by the way, of course, is not determined by what I've just been doing. The coefficient is minus a half. It's not determined by using collinear limits. I've just used that this goes to 0 in a limit, so I can never determine that constant using that technique. But this constant here is the same as that constant there. In fact, maybe I could even call it by the same letter. So the result is the sum over some set of Li1, I5, Li2, I6, Li3, I7, Li4, I8. I've determined all those constants which I wrote at some point. I had a series of constants in front of such a term. In fact, the constants all turn out to be 1 or 0, and the set S, well, the set S simply, the set is somehow as follows. I1 is less than I2, less than I3, less than I8, but we also need that the parity of I1 is alternating. The parity of I1, so if I1 is even, I2 is odd, I3 is even, and so on and so forth. And on a picture, this looks like the following sort of thing. I have an I1, I2, I3, I4, I5, I6, I7, I8. Okay, so this is a result which you can check. You can easily check reduces to, so if I apply this at 10 points, it reduces to this result. If I apply it at 12 points, it reduces to the 10-point result in the collinear limits, and so on and so forth. The next question is it unique? Again, within the ansatz. And the answer is it is unique. And the way to see that is to invent, well, it's a standard thing. It's imagine there's a homogeneous solution. Imagine there's another solution which also reduces. Imagine I have a 10-point solution, R10 twiddle, and both of them reduce to R8. Then R10 minus R10 twiddle reduces to 0. So the question is, can I think of is there a 10-point result which vanishes in the collinear limit? Just like the 8-point did. And the answer is no. And you can sort of, I can tell you that in more detail, but there's this argument here where I constructed the 8-point result using various different collinear limits. You can see it was quite constrained. I had to have every single, every single cross ratio of log there. You can imagine now I've got 10 points that I'm always going to miss something out. If I write down 4 L's, there's always going to be a cross ratio missing. There's always going to be, in other words, there's always going to be a collinear limit missing, which if I do that particular collinear limit, that term will not go to 0, it will remain. And now it's important that I had a basis, because of course I could end up having to add terms together to get 0. But my L's I claim are a basis, so the fact that term by term I don't get 0 means that I really don't get 0. So I don't know if that was clear, but you can think of this more generally at L loops. So in other words, at L loops, the 4L point result will determine everything from then on. So sometimes we were lucky at 2 loops. At 2 loops, the 8-point result determined everything. At 3 loops, the 8-point result won't determine everything. I'll have to go to 12 points in order to determine everything. Okay, if you want me to say more about that, I can do. Right. So let me quickly just summarize the higher loop results, and then try and say a little bit about next MHV. So higher loops, namely 3 loops, in fact. But some of what I wrote down can sort of, you can imagine, generalizes. So this is what we have within our ansatz and with our collinear limits for the 3-loop 8-point result. I can write it as a sum over some set of functions of u1, function of u1, and a function of u2. Sorry, I'm changing the notation a little bit, but we had u14 is equal to u1 minus u15 is equal to 1 minus u37, and I just call this u1. And I have a u26, which is equal to 1 minus u48, and this I just call u2. Okay, there's only 2 independent variables, although there are 4 independent logs of variables. Okay, so this is the result that we get. The method is to write down the most general symbol, which vanishes in the collinear limit. Again, this one has to vanish in the collinear limit. Write down the most general symbol, implement cyclicity, implement parity, and then impose the integrability constraint. And this is the result. I mean, after having done that, you can see that this factorization presumably comes about from the integrability constraint, because u1 and u2 are independent variables. So these are just rational numbers, and the parity and cyclicity symmetry say that a sigma tau is equal to a tau sigma. And by the way, this is at the functional level still. So these functions have to satisfy the following equations. F of u is equal to f of 1 minus u. You see, we've sort of broken the symmetry we had between L15 and L37, but L15 is 1 minus L37. U15 is 1 minus U37, so this constraint brings that back. We also have the fact, and this is the sort of collinear limit constraint really, f sigma of 0 is equal to 0, which of course also means that f sigma of 1 is also equal to 0 because of this symmetry. And then of course I don't really need to say that, but f sigma u is a generalized polylog. It has a symbol. And then the other thing is that the total weight should be 6. So total weight is supposed to be 6. So I could have a weight 3 times a weight 3, a weight 2 times a weight 4. In principle, I could have a weight 1 times a weight 5, but it turns out that I can't invent a weight 1 function with these properties. And then you can just write down all the functions, and there aren't that many of them. So you can write down the symbols of the functions, in particular the weight 3 functions are simply, so the symbol of f1 with this property is equal to u tensor 1 minus u. I'm going back to not including the logs in the symbol. Plus u goes to 1 minus u. And then other possibilities. So basically u tensor 1 minus u tensor u and 1 minus u tensor u tensor u. There's 3 possibilities of weight 3. There's only one possibility for a weight 2 function. It's namely log u times log 1 minus u. And in fact, this is, so you can see how this, I can actually view this as an L loop ansatz. So this works for 2 loops. The 2 loop result I had before can also be written like this. It has to be weight 2 times weight 2, a function with this property. The only function is log of u times log of 1 minus u, and then I come back to this form at 2 loops. So we can imagine, I mean, this imagine this at L loops. Okay, but at 3 loops we find that if we insist on only weight 3 times weight 3 functions, then there's basically 6 unconstrained coefficients still. If we also allow weight 2 times weight 4, there are 7. So we have 6 plus 7 unconstrained coefficients. And then we can try and constrain those further. One particularly nice way of doing that is to use this result of GMSV, Gaotto, Maldacena, Sever, and Vieira, who discussed a near collinear limit and related it to an OPE. They give you a bit more information about what this function should look like near a collinear limit. So I've been discussing really going to the collinear limit precisely. They expand slightly away from the collinear limit, and I can get more information from there. This is consistent with their result, which is of course nice. Unfortunately, it only kills 3 constants. The other constants sort of aren't seen by their limit. Okay, now this thing, of course, I can then lift this to higher points, and again, this should also work for higher loop level as well. But maybe I won't write that down. I'll move to next to MHV.
So what's the final number of unconstrained coefficients in the other?
Well, again, it depends how you count, but I have let's see. I think there's 13 to begin with, and then I can get rid of. No, you can get. Sorry, you can get rid of more of those. 3 of those are determined. 3 of those are determined to be non-zero by the OPE limit. Some of them are determined to be 0 as well. I can't remember the precise number now, but it's something like 8. I think there may be 7 or 8 left after doing this. There's still a few left. Now, one thing I'd like to assume further, but the motivation isn't particularly strong, is that I have a weight 3 times a weight 3 always. That would be a nice thing to have. It's there's this Q-bar equation which of Simon Cohen Hewitt, which relates these, and also Matt Bullimore and David Skinner, which relates these things eventually to tree level objects. And there it looks like the R invariants seem to factorize it with equal number of left and right terms. And I hope if I follow that through, that will correspond to these things having equal transcendentality. But that's very speculative. But that would be nice anyway. Then I would have 6 coefficients, and 3 of those would be determined by the OPE. So we'd just have 3. But that's actually that's getting slightly towards what I want to just say a few words about now. This will probably be mainly for the experts, I'm afraid. But okay, so yeah, are there any further questions on that? Yeah.
Just about the form of this ansatz.
Yeah.
Do you expect that this finite sum of factorized quantities to hold to all loops?
Well, I think within this assumption, again, this is something I've only thought about in the last few days. Actually, we didn't think about this before, but it seems to me that that's quite likely within our assumption. But I don't want to make a definitive statement.
Which assumption? I mean, isn't
the assumption
that was your assumption? So I was.
Sorry, no. This is the result of the assumption. The assumption is that log u's appear in the symbol only.
Okay. Yeah.
And within that assumption, this should be what I get. Now, of course, we've been hearing about all sorts of things that can appear at higher loops, like elliptic functions and so on. And so, I don't want to be I'm making clear my assumptions, and this is the result of the assumptions. So we have to wait and see really what comes out, I think. But the two-loop I never mentioned the two-loop result. Of course, has been confirmed in lots of ways. First of all, it was confirmed numerically, and then later the symbol of the endpoint two-loop result has been found by Karen Hewitt. And in the 2D limit, it reproduces this result. As of yet, the symbol of the two-loop result in general, the function of the two-loop result is not known in the general kinematics. Okay, so let me say in 5 minutes a little bit about next MHV. So in next MHV, there's a structure which involves these R invariants, which in the twistor notation are written like this. Lionel talked about these yesterday. And it should be these times polylogs. This is in general kinematics. Okay, so what happens in 2D, in the 2D limit? Well, there's a problem actually immediately with this guy, because this guy is defined to be it has a delta function, it has some chi I, and then some 4 brackets j k l m plus dot 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 dot, and it's divided by lots of 4 brackets. Now the point here is that this depends on five particle numbers, so I can't have a nice split between even and odd. I'm always going to have 3 of one and 2 of the other, and therefore some of these 4 brackets are going to involve not 2 odd and 2 even. These things only remain finite if I have 2 odd and 2 even in 2D. So this basically diverges. However, the way out of that is given by, well, there's this work of Grisha, Kotemsky, and Sokichev, and perhaps others are discussing spurious poles. And it turns out that these divergences are very closely related to spurious poles. There are a certain subclass of spurious poles. So the 2D limit diverges because this R invariant has spurious poles, which are seen in this limit. So in other words, the fact that they're spurious means they're not really there. So I should be able to get rid of them. And indeed, the way to get rid of them is to consider this object, ij minus 1j, k minus 1k, plus jk minus 1k, I minus 1i, plus k, I minus 1i, j minus 1j. So this doesn't look like the most general thing. I mean, somehow the j and k's and l and m's often differ by 1. And this is finite in 2D. And in fact, it can be written in the following way. Epsilon A, B, C, D. These are SU4 indices. I minus 1, j minus 1, k minus 1. I'll define these 3 brackets in a moment. I, j, k. CD. So where the 3 brackets I, J, K, A, B are equal to chi I, J, K plus dot 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 dot. They're similarly to this thing, but with just 3 indices. Chi I, J, K plus chi J, K, I plus chi K, I, J with an A index, and then the same thing again with a B index. And I divide it by the product of brackets. Okay, so this is an object. It still has some SU4 indices, but apart from that, it looks very similar to the 5 bracket over there. So we, and the point is this has to, somehow the amplitude has to combine into combinations of this form. And we know that because of the spurious pole argument. The thing has to not have spurious poles. And these, in 2 dimensions, these, it's precisely those spurious poles that are making this diverge. Okay, so we can then write down, essentially what I want to say is that I can now go back to my linear algebra thing. I now have a tensor on the one hand because I have polylogs here. At the level of the symbol, this is a tensor. And now I have some other objects in the game, which are these 3 brackets. As you can see, this will be a sort of a right-handed one, and this will be a left-handed one. This could be 1, 3, 5. This could be n2, 4. So these will be even, and these will be odd. Okay, now I want to try and make this make a connection between polylogs and these 3 brackets. And this is how that works. I consider, instead of, okay, so my ansatz now is I have something like ijk, and then I have some other 3 brackets. These are going to be, let's say, even. Then I have a lmn, and then I have a symbol. Then I have a tensor involving L. So this is my linear algebra problem for the next MHV amplitude. Now I want to instead define the following object, m, ij, kl, which is ijk minus ijl. Now it turns out that this has many similar properties to the object that I called lijkl, the log of a cross ratio. Namely, it has the following: m ij kl plus m ij lm plus is equal to m ij km, which is also satisfied for the L's. Now, for the L's, we had Lij kl is equal to the sum of Lij's, and the sum is easy to find. It's just I from I plus 1 to j minus 1 and so on. The same thing is true here. I can define an Mij in the same way as I define the Lij, and I have a sum of Mij's. Okay, so I can define these objects Mij, which look similar to my log of Uij. And more importantly, they have the same property under collinear limits. And given that collinear limits is what I'm mainly using, this can be quite useful for constructing things. So, so the MIKs are similar to the LIKs. There are, however, a few differences. One is anti-symmetry. So I have an LIK is symmetric, whereas the MIK is anti-symmetric. I should say here that what I'm trying to do, maybe I did say that, is obtain a basis now for the M's, just as I did for the L's. The Lij's were a useful basis. I want to try and find a basis for these 3 brackets. So that's the main motivation for what I'm doing at the moment. It looks like I might be not spanning the full set of IJKs by considering differences. You might imagine I'm missing something out. And so in fact, it turns out that's not true because of the following: MIJKL anti-symmetrized turns out to be 2/3 of JKL. So I can always consider, instead of 3 brackets, I'm always allowed to consider m's if I want to. So this is a difference between L and M. Now the other difference is that L, I plus 2, this was log of U, I plus 2. This was a log of a cross ratio where 2 edges were too close together. And this turned out to be infinity. Whereas M, I plus 2 is well defined. It's simply this bracket, I minus 1, I plus 1. I plus 3. But that also isn't necessarily a problem. When I constructed my amplitudes using collinear limits, the infinity was always covered by it had to be covered by something which was 0. So it doesn't matter that here I have something finite. It will be multiplied by something 0. Now it turns out that these MIKs are still not quite a basis. They're not quite independent. Yeah, sorry, yeah. Did you send? Oh, there's a sign there. You need to hold it high. Okay, the MIJs are not independent mainly because of this. There's a constraint. MIJ, J runs from I plus 2 to I minus 2. But I can solve this constraint, and the outcome of this is that my basis. So my basis for MHV were LIJs, where mod I minus j is greater than or equal to 4. My basis for next MHV will be MIJs, together with, it turns out you only need one extra guy, which is a bit annoying. But there's one extra guy in my basis. So if I can somehow argue that I get rid of this guy, then I can use my MIJs. Now let me just write down one formula which will illustrate why I'm discussing all this. And then I'll stop. So we have, so yeah, recall I had R8 at 2 loops. Sorry, this is Rn at 2 loops. I wrote as a sum over S of Li1, I5, Li2, I6, Li3, I7, Li4, I8. And now for next MHV, one loop, I can immediately, without doing any calculation, because of the fact that the m's have the same property as the l's under collinear limits, which I haven't really had time to discuss very much, but it's true anyway. I can write down the sum. I convert 2 of these l's to m's. And this should be the answer for next MHV1 loop. Simply because this is the unique uplift of essentially 0 at 6 points. I'm using exactly the same techniques I used at MHV. One loop. There's 2 m's. There's 2 brackets, and then 2 logs. So again, for those of you who've looked at this Q-bar paper of Karen Hewitt, it looks kind of similar. It relates L loop. So then the dream is somehow to convert L's to M's to make some sort of direct process like that. Now there's this Q-bar equation that people in the audience have come up with, like Matt Bullimore, for example, and that relates very similar objects. It relates, in fact, it relates. This is endpoint to endpoint. So they sort of somehow relate the same 2 objects, but also involve a collinear limit at the same time. They reduce the number of points. But nevertheless, I'm trying to understand if there's any relation between these 2. But yeah, I haven't got very far yet. Okay, thank you.
Few short questions.
Hi.
Do you know if there's can you write the expressions for tree amplitudes, like n squared and stuff, in terms of these finite, this 2D finite?
Yeah, n squared is n squared is a bit not nice. I mean, so for next MHV, I can write a formula in the following way. So it's quite a nice formula.
That'd be great.
Right, I think it's ijk. Oh, 1jk. So at tree level, we have, you often get this thing where it doesn't look cyclic, right?
Yeah.
It's 1jk and then an m and then an l. Sorry, and then an mjk. That's the sort of the nicest way I found of writing it. So this isn't actually written purely in terms of the m's. I could then rewrite this in terms of m's if I wanted to, but this is the nicest form I've got. Now at next MHV, the other thing is, by the way, there's Simon Cohen Hewitt and he looked at this 2D thing in their paper, and they did a bit more than what we did. They got rid of these indices. So I mentioned these brackets for me have indices. They got rid of them by doing a similar thing to the chi's that I did to the twisters. They say chi even has a 0 and a 0, and chi odd has a 0 and 0. So it's not clear to me whether that's a good thing to do or not. Sorry?
You still have all of the chi's?
At the moment, yeah.
Oh, okay.
At the moment I still have all the chi's. So I wrote down the formula somewhere with an epsilon A, B, C, D.
Yeah.
And a bracket with an AB and a bracket with a CD.
Right.
The full SU4 is somehow still there. And some things become 0 if I do the Simon Cameron Hewitt limit. So, for example, R6 next to next MHV. So I would write something down like 135,246 squared. And I can do that because I've got indices floating around. But if I don't, I mean, if this is a delta function, which it is for him, then I get to do that. So, yeah, but the next image is, yeah, we're looking at it, but it's not quite as nice as I was originally hoping.
Any more questions?
If you replace the L with some M in that formula, do you get anything?
Yeah, exactly. That's the sort of thing you'd want to do.
Yeah, that's what
you want to get. That would be next to next MHV.
Because it would have collinear limits which are correct.
Exactly. So I think the point is this crucial point here. That would be all fine if I was allowed to just get rid of this annoying extra term in my basis.
Okay.
But these things do appear, and in fact that's why.
Sorry, just to, I'm not sure I follow completely. So that term does not appear in that sum?
Yeah, so in next MHV I can actually argue why this thing can't appear.
Okay. But it's specific to next MHV.
It's specific to next MHV, and the point is because I've got M's and L's. I know that the analogue of this doesn't occur for the L's, and I kind of need two of them in order for it to work, the collinear limit to work. So,
I see.
but as soon as I have all M's, then I can't use that argument anymore.
If you're a little bit allergic to symbology and you want to actually do the integrals, does the reduced kinematics give you a hand in doing the integrals? Or?
Well, so far, at the loop order that I'm talking about, these are all functions. I mean, I wrote down some symbols, but the only symbols I wrote down were weight 3, and they're kind of trivial to...
Yeah, no, I was just thinking more that if you hadn't heard of symbols
Right.
and polylogs and so on, you actually just wanted to integrate out the loop integrand. I mean, does the restricted kinematics actually help you do that integration, or is it?
Oh, you're talking more of the calculation.
Yeah.
Okay. Yeah, I think it does, but it hasn't. Nobody's really done it. I mean, actually, I've had a go, but well, actually, one loop it does. One loop, everything factorizes.
Directions relatively straightforwardly, just because there's nothing happening in those two directions, but
Yeah.
maybe that intuition isn't right.
So the one loop, for example, the Wilson loop gluon propagator actually factor. You have an integral over sigma and tau, and the at the level of the integrand that completely factorizes into two 1D integrals.
Oh, so the Wilson loop actually gives you a...
So I get log. Normally I get Li2s. In 2D kinematics it becomes log, and you can see that at the level of the integrand. Beyond there, it's not so simple.
Somehow, since there is no external kinematics in the remaining dimensions, in those dimensions, it's like there is an internal mass that you have to integrate on.
You mean one loop?
Yeah.
Yeah. So that's.
Yeah.
So there's some simplification.
Okay, any more questions? If not, then let's thank Paul again.
Okay. Thank you.